In the last lecture, we have learned what is intersymbol interference, and we have learned the techniques to mitigate intersymbol interference. And one of this technique is pulse shaping filters. Uh, and the other technique we learned today is equalization technique. So first we learn the summary of the last lecture. Uh, we know that the transmitter and receiver response ideally should be a low pass filter, and that would be the impulse response of a sinc function. And we have subsequent pulses transmitted in the form of sinc pulses. So so the input of this low pass filter is the sequence which we want to transmit, and the output would be a sync like pulses, and these are the subsequent sync pulses which are sampled at appropriate timing instant, which is equal to the symbol duration t. So we know that the minimum bandwidth required for this low pass filter is 1 by 2t. So, but we cannot implement the ideal low pass filter. So we have to assign some shape to this filter. So this shape would be a cosine shape, and for this we need the roll-off factor. And the roll-off factor of the filter reflects the excess bandwidth we utilize for this filter. So the roll-off factor would be 1 if we are using 100% excess bandwidth, and the excess bandwidth will be 1 by t in that case. We have learned this previously. So the response of the impulse response would be 2 omega naught sin 2 omega naught t. If we substitute the value of omega naught equal to 1 by 2t, so we will get the response h of t by 2 omega naught is equal to sin t by t, which is the desired response. Actually, these filters are cosine or sine-like shape, and we have seen that how we implement it by multiplying it by a cosine factor, having the corresponding roll-off factor. So we also learned in the last lecture that the transmitter and receiver response would be equal to the root raised cosine filter, so that the product of two will be a raised cosine response. But we didn't consider the effect of channel in the last lecture. So if we consider the effect of the channel, then we need to equalize it. So in that way, that the both response would be equal to 1. If both response would be equal to 1, then we are able to receive the sync-like pulses at the receiver, and we have no intersymbol interference at the sampling instance, which is equal to the symbol duration t. At the moment, we are considering that we are taking one sample per symbol to estimate the symbol. So the channel will in fact distort the sync pulses, which we transmit over it, and we have the distortion in the symbols or pulses, and that distortion would be produced like positive or negative echoes. So due to these echoes, we have intersymbol interference at sampling instant t is equal to kt. So to mitigate this effect, we introduce the equalization technique. So here you are seeing that we have the equalizer. So what will be the response of the equalizer? That would depend entirely on the channel response. So if we see that the channel and equalizer response would be equal to 1 if we produce the inverse of the channel response by equalizer. So in short, we can say that the equalizer response is inverse of the channel response. If the channel response would be HCF into EJ theta CF, then we have the equalizer response would be the inverse of this as mentioned in this equation. So the magnitude would be the inverse of the magnitude and phase would be inverted. So there are two types of channels which are static in nature, or we can say which are time invariant, and there are channels which are time variant and are not static. Their behavior will change by time. So these two cases are considered by considering the wireline and the wireless communication channels. In the wireline channel, like we are considering a DSL connection over the copper pair. So for transmission of data over such a channel, it will remain static for a longer period of time compared to wireless channel. But why we need equalization in this case? Because the channel behavior is unknown. So we need to estimate the channel behavior in that case also. But in case of wireless, we consider a mobile phone user in a car. So in this case, the channel is highly time variant, and this kind of equalization is called adaptive equalization. Equalization has some problems. Sometimes sometimes it is not possible to generate the inverse of the channel response because the channel response is zero at some frequencies and the inverse would not be defined. The other problem is that the equalizer can have infinite impulse response even if the channel has a finite impulse response. So in that case, the impulse response of the equalizer needs to be truncated. So in terms of time domain case, we consider uh, a FIR channel with non-minimum phase. That means that all zeros are within the unit circle. The inverse of this is the poles outside the unit circle, which causes instability. To overcome this problem, we use all pass decomposition of the system to make the system having stable inverse. Secondly, if we assume that the noise at certain frequencies have a very high gain, so the impulse response of the channel or having zeros near the unit circle will create poles of the equalizer which are outside this unit circle. There are different types of equalization in which there is linear technique, which is linear transversal filter. It is just an FIR filter, and we will see it later on. For FIR channel, equalizer output is infinite impulse response. To overcome this problem, we use adaptive FIR filter. And the infinite impulse response needs to be truncated to solve this problem. In decision feedback equalizer, we are estimating the errors on the basis of feedback path, and we are trying to minimize this error. So these are used for time variant channels and are adaptive in nature. Maximum likelihood sequence estimator is, in fact, we are trying to estimate the sequence instead of a single sample. So this structure is complex and it is very difficult to implement. So this is the case of linear transversal equalizer. So in linear transversal equalizer, this is the input of the equalizer, and the input of the equalizer will be delayed and multiplied by different coefficient weights, and we will generate the sum to get the output of the equalizer. So in fact, this is an n tabs in this filter, and the order of the filter is n, and it is an FIR filter. So so in this we calculate the overall delay of the filter would be 2n tau. Why? Because if we have delay coefficients from -n to n, so we have the total number of taps equal to 2n plus 1. So the delay tau is equal to the symbol duration, and we have taken its value equal to t. So mathematically, we can represent it by this equation, and the value of the value of k spans from -2n to 2n because of this input sequence is in fact is the convolved sequence with the version of itself. So this convolved sequence has length n plus m minus 1, or roughly we can say we can sample the input of the equalizer from -2n to 2n. But we have to estimate that what value of n we will choose as long as we can consider the effect of infinitesimal interference, because the value of n would be larger will make the equalizer structure complex, and higher order FIR filter will be difficult to implement in the hardware. So what will be the desired output? The desired output would be such that for k is equal to 0, we need the value 1, and for all other values, we need the output of the equalizer would be 0. If we have non-zero values, we will change the coefficient weights. So we adjust the coefficient weights that all non-zero values would be 0 except k is equal to 0. So there are two types of equalizers: preset equalizer and adaptive equalizer. Preset equalizer, we used a training sequence. The initial training sequence would be already stored at the receiver, and this training sequence will compared with the transmitted training sequence in the start of communication, and we estimate the coefficient weights for the next communication. In adaptive equalizer, we are periodically estimating the coefficient weights, and this is based on the feedback path. To make a robust equalizer, we have a training mode and the decision directed mode. For training mode, a known sequence is transmitted, while decision directed mode, uh, at the end of training mode, the adaptive algorithm is turned on, and we adjust the coefficient weights according to the channel response. If we see the impulse response of the transversal filter, so it would be like this. So in fact, we have we incorporate delay. We incorporate delay. We considered this delay is equal to the symbol duration, and we, as long as we consider the effect of ISI, we set this value of n, and this spans from negative n to positive n, and the coefficient weights would be uh, adjusted according to the according to the desired output. We have seen that the desired output at the kth sample would be uh, equal to 1 when k is equal to 0, and 0 for all values of k not equal to 0. So in frequency domain, this delay can be uh, considered as a phase shift. So this can be considered as a phase shift. So this is the equalizer response in frequency domain. So to set the Nyquist criteria for zero ISI, we have chosen that this output would be 1 at k is equal to 0 and 0 for all other values of the coefficients. So since there are 2n plus 1 coefficients, we express this in the form of matrix. So that matrix is y is equal to xc. So x is in fact is the input of the equalizer and y is the desired output of the equalizer, and c is the coefficient matrix. So here these are considered as matrix. So we are considering that the k spans from -2n to 2n. I already told you the reason that the symbol is convolved with its own version. So the length of this convolved sequence is -2n to 2n instead of -n to n. And this X matrix would be in fact is twice of 2n plus 1, and this would be 4n plus 1 into 4n plus 1 matrix. So C is the column vector of 2n plus 1 and Y is the column vector of 2n plus 1. So we need to truncate the X matrix to 2n plus 1 into 2n plus 1. So if in the previous case, if we consider the value of this tau or the value of this tau is equal to t, so this is the symbol spaced equalizer. And if we consider this value less than t, that is fractionally spaced equalizer. Fractionally spaced equalizer means that we have multiple samples per symbol to decide the symbol value. So there are different solution for this linear traversal equalizer. One is with the zero forcing solution. So this zero forcing solution, if we consider n is equal to 1, so that would generate equations from this y of k, and that equations in fact for k is equal to -1, 0 and 1, and for n that is equal to -1, 0 and 1. So we can expand this equation to have the results here, and we have the value of n. The value of n is -1, 0 and 1, and value of n is -1, 0 and 1, and here also we have the value of n is -1, 0 and n. And for k is equal to -1, we have the value of k is equal to uh, minus uh, sorry, this is in fact is n, and this is in fact is k. This is in fact is k, and this is k minus n. So k is equal to -1. We have -1, -1, and -1. So in fact, what you see is that you have the value of x of 0. You have the value of x is equal to -1, because here -1 plus 1, 0, and you will get it x of 0. You will get it x of -1. You will get it x of -2. X of -2. So this is in fact is the delayed version. So if you are considering, so you are considering the effect from -2 to x of 2. So in such a way that first you have x of 0, x of -1, x of -2, then you have x of 1, x of 0, and x of -1, and then you have x of 2, x of 1, and x of 0. And you multiply it with the coefficient matrix C of -1, C of 0, and C of 1. When you multiplied it, you will get the desired output. So this matrix is, as I said earlier, is truncated from 2n plus 1 into 2n plus 1 because of the size of the column vector 2n plus 1 into 1. And this is also a column vector of 2n plus 1 into 1. So if we substitute the value of n is equal to 1, so it is 3 into 1 column vector, and this is 3 into 1 column vector, and this is 3 by 3 matrix. For n is equal to 2, we have the expansion like this. So simplifying these results, they have the coefficient is equal to x inverse of z. So what we will have, we will take the inverse of the input matrix, and we will have the desired output. We will have the desired output. So this desired output is a zero forcing solution that we will force all the undesired values to be zero. So we will have this value to be 0 and this value to be 0, because for this n not equal to k, And for this, k is equal to 0 or n is equal to k. And similarly, we have the value of z is uh, 0 for n not equal to k, or for all other undesired values. So we have its value equal to 0. So what we are forcing here is we are forcing the output to be 0 at all undesired instants where we want no ISI. So that's why this is called the zero forcing solution. Zero forcing solution will cause noise enhancement. So if we have the received sequence in that way that we have this is the noise and this is the delayed version of the symbol, and this is the this is the uh, this is the output of the equalizer. So what we will see here that we have the signal f of 0 s of n, that is the desired value, and for all other values from k is equal to 1 to l, so we have the intersymbol interference, and this is the noise. So when we write it in the z domain, when we write this equation in the z domain, so we have f of z, s of z plus v of z. So the equalizer weights would be the inverse of the channel. So that would be c of z divided by 1 f of z. So what we will get, the estimated signal of the equalizer would be c of z into r of z, and we will get this value cancelled and we will get s of z, and this f of z here would cause noise enhancement due to the frequency nulls of the channel frequency response. The other solution after zero forcing solution is that we calculate the minimum mean square error based on the coefficient weights. So mean square error is in fact is defined as the square difference between the desired data symbol and the estimated data symbol. So this is in fact is the output symbol and this is the estimated symbol. So that difference is the error and the square of it is the mean square error. And we this mean square error is in fact is the expected value of the square of the error. and we can expand the square of this z of x minus x of c in that way that it would be the equation like this. You can try it yourself. So this would be z square n, and xc square would be cc transpose, and x square is x transpose x, and minus 2 z of n x of transpose into c. So when you have the expected value of z square n and the expected value of x transpose x and z transpose x, so you have the autocorrelation matrix Rxx, and you have the cross correlation matrix RCX here. And we try to minimize it to 0. So when we try to minimize it to 0, so what is in fact this equation will be reduced to 2Rxx C minus 2Rzx is equal to 0, or roughly you can say that would be the coefficient would be the inverse of this cross correlation matrix. Sorry, inverse of this autocorrelation matrix and into this cross correlation matrix. So in this that way you can have the coefficients calculated from the minimum mean square error solution. So this is an example that you have the length of the sequence, which is 7 tab. You have values from 0.0108 to 0.0110. So you have to apply the minimum mean square error solution to find the coefficient weights. Of course, this is a large matrix and you cannot solve it on paper. You have to use MATLAB to solve this problem. So this is a large matrix. So for a 7 tab filter, the value of n is equal to 3. So in fact, dimension of matrix X will be 4n plus 1 by 2n plus 1. So in fact, what we are using, you are using the value of k and n. So so you are multiplying and taking it by 13 into 7 size matrix here. So this is the different what we have done in case of zero forcing solution. So this is we calculate the Rxx matrix and Rxz matrix, and we take the coefficient values from this equation, and then we calculate the ISI in the received signal and the value of the maximum ISI and the sum of the ISI from this signal. So this is in fact example 3.6, and you can solve it with MATLAB. Steepest descent algorithm is the another solution because it is difficult to take the inverse of a large matrix. So we use gradient-based iterative approach to estimate the channel coefficients. So what we in iterative approach, we use the initial estimate uh, based on this cost function, and the cost function is same, which is the mean square error is the cost function, and we try to minimize it. And the initial estimate of the coefficient, and on the base of the initial estimate of the coefficient, we update it uh, in the opposite direction of the gradient J. So this gradient is in fact uh, is the uh, derivative of this function with respect to C, and keep on updating the old estimate till convergence is reached. So here we have the value of J. The direction of gradient is in this direction, and we go in the direction opposite to the gradient. And every time the direction of gradient is in opposite direction, and we will move in opposite direction, and moving in this way, we will reach this point, which is the desired point. So this is the steepest descent algorithm, and how will we how we will estimate the coefficient weights by this algorithm. For example, we have the initial estimate of the coefficients. So the next time we estimate it, estimate the coefficients. So that would be Ci minus 1 by 2 mu delta I. So this is in fact is delta I is the uh, value of this matrix, and mu is the step size. So in the instantaneous value of this delta is calculated by this matrix. So if we have the value, if we compute the value of delta I from this equation, so we can also calculate the coefficient weights. So this is in fact how we done it in MATLAB. So in MATLAB we have the you can run this code and learn from it, but the value of mu, the step size is 0.001. By increasing the step size, you may have less iterations, and the length of the sequence. If you take the length of the sequence, if the length of the sequence is large, so it will take more time to converge. So it is, in fact, is that how long the channel impulse response is. So the channel, you can take different impulse response of the channel, and you will see the convergence time of the algorithm. So this is the, in fact, is the steepest descent algorithm, in which you calculate the error from this matrix, and you will calculate the next coefficient weights basis on this error. So every time you run it, so you have the different coefficient weights. Finally, when it stops, you have the best estimate of the coefficients. This is an iterative approach. So this is the diagram that the channel impulse response is shown by this blue line, and the equalizer response would be shown by this red line. So this is almost a better estimate of the inverse of the channel. Training mode and decision directed mode. So I have told you earlier that you have the training signal generator initially, uh, and this will, on the basis of this, you will calculate the equalizer weights, and you compute the error, uh, and make this algorithm adaptive. So this is the decision directed, is, in fact, is the ongoing process. So on, after the after the adaptation after the adaptation, you will have a decision device to estimate the symbol. So it is just like a quantizer. You have implement a quantizer, and on the basis of this quantizer, you estimate different symbols. So whatever you have a symbol set, or you have a symbol space, your equalize on the basis of the equalizer output, you have a decision device to estimate the symbol. So this is, in fact, is the fractionally spaced equalizer. Fractionally spaced equalizer, you have in fact multiple samples per symbol, and on the basis of these multiple symbols, you have the decision of the symbol. So in fact, we are not relying one sample per symbol. We have multiple samples per symbol. Usually fractionally spaced equalizer use two samples per symbol to estimate this, estimate the current symbol. So next, after linear transversal equalizer structure, we have the time variant channel, and for that time variant channel we have a decision feedback equalizer, and that decision feedback equalizer in fact is helpful to eliminate ISI for adaptive channel conditions. So this adaptation based on decision feedback equalizer will be in two stages. One is the feed forward filter and one is the feedback filter. So the basically the feed forward filter is in fact uh, feed forward filter will have the forward estimate, will we have the forward estimate, and this forward estimate would be calculated by this quantizer or detector, and uh, if we have some error in the output, so this error output will be removed here, and this error will be removed from the symbol at this point. So this feed forward filter is in fact is incorporating delays. So there it is nothing but just it incorporate delay. For example, if I say that AN is the input symbol, uh, and then we can say that here this the output of this feed forward filter is AN minus delta, and delta is the delay. So you learned it from the previous case that the delay is incorporated at this point, and this is in fact is forward through the detector, which have just a quantizer to estimate the output from the symbol space. And if there is some error, if there is some error that would be what would be estimated, what would be estimated is in fact is the output of this detector, and that estimate would be whatever is incorporated here, and that estimate would be compensated by summing up here, and this would be uh, adjusted in the next uh, estimation or the next detection process. So once you detected the symbol, what is the correct symbol? So you have the version of it, and you can completely eliminate the intersymbol interference instead of instead you just have the unless you have the wrong detection. So the nonlinear feature in this equalizer is the decision device. Is due to the decision device, which attempts to determine which symbol of a set of discrete levels was actually transmitted. Discrete levels means that we have a quantizer implemented here. And so this will there is two types of ISI. One is the post cursor. For example, we have this like sync type pulse, and we have this is the desired sample, and we have the other values of the sample at these points. This is in fact is the post cursor. So because the post cursor ISI will affect the upcoming symbols, and the precursor ISI will not affect that much because it is already detected. So this type of feedback filter would use to remove the post cursor ISI. So this is the uh, digital cellular telephony. There are different uh, uses of equalization. So the summary of this is the of the among the non-linear equalizers, the decision feedback equalizer is most currently in use. The other ways to implement nonlinear equalization having more complex solution and are not practical implemented in the current systems. So thank you very much for this lecture. So I will upload the related material for further research and reading at the LMS. Stay in touch and keep me informed about your feedback.